So invariably, I look a little bit ridiculous under this camera. So I'm using a thermal imaging camera. And what that's doing is it's detecting infrared radiation from my body, okay, different amounts from different parts of my body, and that's going to a camera which is next to a normal standard camera. And those images are kind of combined to try and generate this weird thing that you're seeing right now. And what it does, it assigns a colour to things. So the more radiation that I'm giving off, the redder it appears. So my face will appear one colour, whereas as will my arms and my hands, whereas sort of my jumper and stuff will appear sort of not to be giving off so much radiation, certainly more than the background. Now, all objects emit radiation, and the hotter they are, the more they emit. And so the sun, for example, very hot, emits lots of radiation. So that is the predominant method by which we get energy through the vacuum of space to us. Energy cannot get to us from the sun via conduction or convection because there is no solid pipe connecting us and there's no particles, or not enough particles in the vacuum of space to generate an effective convection current. So we rely on radiation. And what we're going to look at is how we can affect the amount of radiation that objects will either give off or will absorb, because that kind of allows us to design things either to be able to put more radiation out if we want them to give off their heat, or to not do that if we want them to sort of stay warm and things like that. So that's how one of the things, and that's colour dependent. We're going to look at a few examples of how that works in both sort of directions and so on and so forth. The infrared camera is a little bit weird, but you can't see infrared radiation with your eyes, so we're kind of relying on it. So let's have a look at our practicals.
This first experiment is called Leslie's cube. Okay, it's a metal cube, hollow, and each side has a different colour. And so what they do is they go white, sort of a dull silver, a dull black colour, and then a shiny black colour. And what we're going to do is we're going to put some hot water in, so it's hot, so it will give off radiation, and we're going to look at how that colour, how much radiation we get from each side of the cube. Okay, so I've got to now switch to the infrared camera. And here we go. So I've got my hot water. Let's pour some hot water in. See what this looks like. Now you'll see actually inside, you can actually see where the water level is. So, oop, that was not the right thing. I spilt some. Right, okay. So you can actually kind of see where the hot water is, but if we go around the cube, we will see that not all sides are emitting the same amount of radiation equally. So, okay. So we're clearly getting less radiation from this side, more from this side, and from this side. Let's go around it. And from here. And that side there, that is the silvered side. So the silvered side of this is giving off less radiation. So our camera is detecting less from that than it is from the other parts. Now what's somewhat a little bit disappointing is that we're not detecting, possibly because we're not sensitive enough, well, we're detecting it a little bit. You can probably hopefully see that this here is getting a maximum temperature. It thinks it's around about 88.3 degrees. It's making that estimation based on how much radiation it's detecting. Whereas on this side, it's detecting a slightly cooler temperature. This is the white side. So it is, theoretically, it's looking a little bit less than this one. But this side here, absolutely wonderful. That's certainly giving off much less radiation. So our thermometer here thinks it's colder. It's not physically colder, it just thinks it is because less radiation is seeing it. And that's because shiny surfaces, silvery surfaces, give off less radiation than dark surfaces. So our camera is confused a little bit. Despite the fact that the same hot water's gone into this whole thing, it's certainly feeling that there's less energy there than there was on the other sides. One of the other interesting things we can see, and I'll just do this very, very quickly, is we can see where the Leslie cube was. If we move it slightly, let's move it all the way up here, we'll actually be able to see an imprint of where it was sat. So some energy was leaking out of it via conduction into the table, and we can see the print of where it was. So if you've got a good enough infrared camera, you can actually track where things have gone. Isn't that cool? Here we've got a very similar experiment. This is the Leslie's radiation plate. So what we've got under here is an electric heater connected up to a 12-volt supply. So we're going to heat this thing up, and these are going to warm up. They're going to emit radiation. And so what we're going to do is switch to the infrared camera to get a sense of the different amounts of radiation coming from all of them. But just to be very clear as to what we're getting from each one, we have a shiny silvery surface, we have a slightly dulled silvery surface, and we have a black surface. And we're going to see as they warm up which one starts emitting radiation first and the most. Okay, so I have just turned the heater on, and we're going to see this thing. And what you can quite clearly see very rapidly is this one here is heating up a lot more. So that's the dark one. It's dumping out a large amount of radiation, which our camera is detecting. So it currently thinks it is very hot. So it currently thinks it is, so it sort of thinks it's like 27, 28 degrees. And then we have the next one is the sort of the dulled silver surface. So the silver surface which has kind of scratches in. And then finally catching up is that silver surface at the top. So we have this quite marked difference in which colours emit radiation more effectively. Dark colours emit them really effectively, then, whereas silver colours, light colours will emit them less effectively. And the shinier they are, the better they are at emitting, the poorer they are at emitting radiation. So if you want to dump a load of radiation, thermal radiation out there, cool down, you want something to be dull and you want it to be dark coloured. And that is Leslie's thermal radiation plate. Now, all objects emit radiation. And as you've seen, different colours of object emit radiation, different amounts. But equally as true is when colours absorb radiation. Now, the thing you probably think about almost automatically is what it feels like if you go out on a hot sunny day with a different coloured t-shirt on. If you wear something light, it tends to be cooler. If you wear something dark, it tends to be a lot hotter. This is actually even visible if you have different hair colour. So I'm got blonde hair colour. My hair stays a lot cooler than my brother, who's got dark hair, and in the summer, his hair gets really quite hot to feel. And we can sort of see this in action. So what I've got here is an infrared heater. So it's going to give off infrared radiation. And I've got these two discs. This one here, which is shiny and light, and then this one here, which is dark. Now, it's difficult because we can't really just do this with a infrared, we can't just do this with an infrared camera because of the way it works. What we have instead, let's turn this on, is on the back of these discs is a little thermometer. So a little color graded thermometer which will tell us the temperature that that disc has reached by being in view of this radiation source, this infrared radiation source. So what we're going to do is going to have that running, place these reasonably close, and we're going to see what happens to the thermometer readings on the back. Need to make sure that So here's our experiment, here's it going, and what we've got here, let's move these as close as we can to the radiant source. So they're the same distance away. We'll see what happens to colours. So very rapidly, the one on the left, as you see, this is the dark one, this is the shiny one, and as these colours light up, that's going to tell us the temperature. So we can see already that this has reached the 40, whereas this has only just started colouring in the 30. 45 with the black one, maybe getting to 35. So we can see that the darker disc is getting a lot hotter much more quickly, and that's purely as a result of its colour. Okay, it's a dark colour, it's absorbing that energy, it's got to 65, it's even going to very quickly. It's going to tell us to stop very quickly because the word stop is probably going to light up. And there we go, you can see the word stop is lighting up, so I'm going to pull that away, take it off. That got to 65 degrees, so there it is, the dark one. And we can see this shiny one still warming up, so it's only just hit 45 degrees. So within that very short expanse of time, we saw a very dramatic difference between the radiation absorbed by something which is shiny against the radiation absorbed by something which is dark. And that, when we want to design things to absorb energy or to not absorb energy, that's why we have to be careful about the colours that we are choosing. Shiny, white, light things will reflect a lot of that energy back, whereas darker things will absorb that energy and will gain temperature more quickly. One of the things about radiation is that everything emits radiation. The moment an object becomes hotter than its surroundings, it puts out more radiation than it's taking in. And this can have consequences for devices that we build and why we build them and how we design them. So what I've got here is I've got two kettles. I've got a white kettle and I've got a black kettle. And the question that is which one, if they are the same power output, they came from the same place, they both got a power of, you see, that's got a power of somewhere about 2,000 watts. So they're 2,000 watt kettles. They've got the same amount of water in them. The only difference between them is white, black. So the question is, which one is going to boil quickest if we turn them on at the same time? Is it going to be the white one, is it going to be the black one, or is it going to be the same? So let's try that and let's see what occurs. Right. This is exciting. I mean, you know, who isn't excited by physics, you know? Feel free, share this kind of video. This is what my physics teacher does. It goes into work. Boils not one, but two kettles. My goodness. So you can hear, you might be able to hear, you can hear some of the energy that's being lost via sound. Because what's going on there is we're trying to get thermal energy into the water. And how exciting. I'm running out of things to say now. It's a kettle. Although it is weird. Some people don't have kettles anymore. They've just got the water heaters. I mean, you know, I feel old. I feel very old when I do this. Maybe I should have put less water in. It would have boiled quicker. But never mind. We started, so we'll finish. So see what we get to. Let's have the excitement. Let's get in. See this. Very exciting. Let's have time. So we'll notice when they finish because they will click up. Okay, now I'm starting to see some steam coming out of them both. And what you might start noticing is that a lot more is coming out of this one than starting to come out of this one. I mean, I've never been this excited by a kettle boiling before. And the surprising thing is I can't make tea using them because they are covered in gunk on the inside. So, never mind. Let's go. Come on. So yeah, you can probably see the steam that's coming out the top of both of them. Always change your mind. Now we're getting to the point which, if you know kettles like I know kettles, we're getting close, and you can see the liquid is now boiling inside the white one. And let's see what happens. One. Okay, so that's one gone. The white one is gone. That is a quite significant difference on two kind of half-filled kettles, or just over half-filled kettles. That was a difference of around about, it seemed to me, I can go back and look at it, but 15, 20 seconds. So 20 seconds extra to boil this one, purely because of the colour of the kettle. That's 20 seconds extra of electricity that you're using, which is 20 seconds extra of 2,000 watts, so 2,000 joules every second. So that's 40,000 sort of extra joules that have been used simply because you wanted a black kettle. Now, why does that occur? Well, it's because of the difference at which colours radiate their energy away. So when this is a situation where the hot thing is on the inside of the kettle, the kettles are filled with hot water. So they're going to radiate their energy out. The black kettle is really good at doing that. So it is dumping energy into the air around it via radiation, so into sort of the surroundings via radiation, much, much, much more effectively than this one. But the thing is, we don't actually want that to happen. We want the energy to be maintained inside the kettle. We want the kettle to hold on to that thermal energy because we want the water to get hot. And so what we have in this scenario is something where often people design things the wrong way around. They paint things like this, or they have things in a certain colour because they have a preference in that way. But this is the difference of radiation due to colour being put out, and it's one of the most sort of like impressive. It's straightforward but quite a nice, impressive little demonstration. Now, if you examine things wherever there's an attempt where you want to get rid of energy via radiation, and that's something you want to happen, tend to be colouring things in black. So radiator fins inside a computer system, or something where something's going to get very, very hot, dark colours. That's what they use because they want to dump that energy out as effectively as possible. If you want to design something to not do that, you're using light colours. And there we go.